Okay, then what kind of algorithms do we have in deep learning? So when deep learning was just beginning, then we could organize all these deep learning algorithms in this way. So since we used pre-training, so we need building blocks to train the layers. Okay, so RBM was the most popular, and the autoencoder can be used, and some people use the sparse coding to train the layers, layer by layer. And then we can stack these layers to make deep networks. So we can make deep belief networks or generative stochastic networks and deep Boltzmann machines. All these models are generative models, which means we can generate some data, okay, not recognizing some things. Okay, and recently we have variation autoencoder and GAN. And for discriminative models, which means we can use these models to recognize some things, we have CNN, convolutional neural networks or recurrent neural networks. But interestingly, this CNN was proposed in 1989 and the RNN was proposed in 1986. And even the LSTM, which is the most popular recurrent neural network model, was proposed in 1997. Okay, so these discriminative models were proposed a long time ago, even before this deep learning era. Okay, but now recently things have changed a lot, so I'm not sure that we can make these kind of categories because we use RNN and CNNs in the middle of generative models and so on, and we don't use building blocks anymore most of the time. In these discriminative models, the most of the time people are interested in the recognition, image recognition or speech recognition or some other recognitions. So CNN and RNNs are most popular network architecture. And also recently Transformer is quite popular. But let's talk about the CNN and RNNs really briefly. Okay. First, convolutional neural networks. CNN is actually a class of deep neural networks and it can be applied to image recognition. And recently it can be applied to speech recognition and neural machine translation, etc. So CNN was applied to image classification first, and then it had a huge success, and it won a lot of competitions. ImageNet and Kaggle facial expression recognition and German traffic sign recognition, handwriting recognition. It was one of the best algorithms. Okay. And even in the beginning of deep learning era, CNN was one of the few models that can be trained purely supervised. So CNN didn't use any pre-training from the beginning of this deep learning era. And CNN was based on this neuroscientific discovery. Hubel and Vigel discovered this simple cell and the complex cell in our brain. Okay, actually cat's brain. So given this image, then they found we have simple cells and the complex cells, and they understood how this simple cell works. Okay, so basically simple cell is kind of edge detector, and the complex cell is a little more complicated than the simple cells, but it's like a pooling. Okay, it's or subsampling. So in the CNN, actually we took this neuroscientific discovery as it is. So we have input and we have kernels. So the same column means the same parameter. So in this case, we have 6 parameters, even though we have lots of connections between the layer H and layer H plus 1. So when we have 5 input nodes like this, and 6 hidden units like this, then if we have two maps means we have one map and another map, then if it is a fully connected neural network, then we need 30 parameters. But when we use a CNN, then we need just the 6 parameters. So we can reduce the number of parameters a lot. And also, we can make a connection locally. Okay, so this one, it has nothing to do with these two nodes. And this one has nothing to do with these two nodes. So they actually focus on the local area. And think about the image recognitions. So in the first layer, if they are edge detector, then they don't have to look at all the image. Okay, they can actually focus on the small local area. Okay, that's what they need to do. And then in the upper layer, they can actually combine some more areas. And then in the next layer, they can combine more areas. And finally, they can look at all the areas at the same time. But at every layer, they can focus on the local area. That's the beauty of this CNN. So they have local connections, and also they share the weight. As I said, the same color means the same parameter. And first, Yang Kun proposed this LUNET, which is the first CNN model. And it's quite simple. Given this image, we have a convolutional kernel first, and then we apply the max pooling. And then we have another convolution layer and max pooling layer. So each layer is quite simple. So we have lots of simple layers, and finally we can recognize the output. Okay, it was in 1989. And then in deep learning era, Alex Krisky proposed AlexNet in 2012, and it looks like this. We have first convolution layer and the max pooling, and the next convolution layer max pooling. So we have more layers. So basically, it's bigger CNNs. There is not so many new tricks or techniques here, but he had to spend a lot of time to implement these big network. Back then, it was a big network with 2 GPUs. So there are a lot of implementation issues. So he spent a lot of time, and then more importantly, he trained this network for around 1 week. Okay, that's pretty much it. And recently, we have a lot more CNN models, but these CNN models are basically a bigger model than the AlexNet with a little more tricks, but basically the same architecture. Okay, and then the next one is recurrent neural networks. And recurrent neural networks are different from other feed-forward neural network or convolutional neural networks in a sense that it has a memory effect. Okay, so look at these feed-forward neural networks. And in this case, even though I put this time subscript, it doesn't have a time here. So given x, and then we can have h, and then we can have a y. That's it. It's simple. Even when it is the convolution layer, then still when we have x, then we can have h. But in recurrent neural networks, as the title says, we have a recurrent connection here. So the equation is slightly different from here with this new term. So now t means something here. So ht is a function of x sub t and h sub t minus 1. So when we compare these two equations, this is the new term and the other terms are exactly the same. Okay, but by adding this term, we are adding the memory effect, which means the current state is based on the current input and the previous state. Previous state means the memory, the past information. That's basic equation of recurrent neural networks, actually the conventional recurrent neural networks. And with the recurrent neural networks, we can do a lot of things. Okay, so this one is a DNN. So given one input, then we can have one output. That is DNN. But with RNN, we can have many different types of mapping. So we can have one-to-many and many-to-one and many-to-many and another type of many-to-many. So these are examples, okay? So think about the image caption generation. We have one image, then we have to generate a sentence. And the sentence is a sequence of words. So one word, then second word, then the third one, and so on. So it is one-to-many mapping. And think about the text categorization. We have words as a text, and then we have to recognize what kind of class the text belongs to. So we need the classification at the end of this RNN. So that is many-to-one mapping. And machine translation is many-to-many mapping because we have input sequence, input the source language sentence, and then target language sentence. Okay, so we don't have to have the same numbers here. When we have 3 words, sometimes we can have 2 words in the target language or so. And in this case, there is a kind of time shift here. So when we have the last word for the source language, then we can start generating the first word of the target language, right? Because we need all the sentence. Because sometimes, the language pairs might have different order of the words in a sentence. So we have to wait until the source sentence is done. But in speech recognition, when we have one input, then we can recognize one output. This one is not the end-to-end speech recognition. Okay, this one is actually acoustic model. So given one like a 10 millisecond, then we can recognize which phoneme this belongs to. Like is it A or is it P or is it L kind of thing. Sometimes we have a P P P L L L for Apple. Okay, but anyway, it is many to many and there is no time shift here. Okay, that's how we use RNNs in many different applications. And the conventional RNN has a memory effect, but the memories fade away over time, like this. So when we have input 1, and then after this 1, we have a 0, 0, 0, 0, 0, 0. Then even though this hidden state has some memory effect, but the memory will fade away over time, like this. Okay, so we can lose some information even when we need that information here, but we cannot have that information. So LSTM was proposed. Okay, so in LSTM we have 3 gates, and these gates will control this information flow. So if this one is open, then we accept this information, and then if this one is open, then we pass. If this one is closed, then we don't pass this information to the output. And then next, if you don't like this information, then we can close. Okay, and then we can keep this information and again and again. And now if we want this information at the output layer, then we just open the gate, and then we have the same information here, and then we pass and we pass, and when we need, then we can open. And if we open this one and we close this, then this one will be here. So we can control this information. And the next one is generative models. The first generation of generative model is DBN, Deep Belief Networks. So they train the neural networks based on the RBM, layer by layer. Okay, and then they combined and then they trained. But important thing about the generative model is that it can have a mind if it can generate some samples. And the internal representation of external world. So the mind can be interpreted as internal representation of external world. Okay, so we look at the external world and our brain has internal representation of an external world. So as long as we have internal representation, then we can imagine something. So imagination is actually generation. So if the model can generate the input, then we can say this model has a mind. So that's a simple understanding about the mind. So given this MNIST data, then we can generate this same image based on this network. And recently we have better generative models. So we can actually summarize recent generative models like this. First, we have autoregressive model. And second, we have VAEs and then the GANs. And then recently normalizing flows. Okay, so they have their own pros and cons. So if you're interested in any of these algorithms and models, then you might have to take a deep learning class.